Thank you, and a huge thank you to all the organizers of the session and the conference. I've really enjoyed the huge diversity of talks that we've seen over the last couple of days. To introduce myself, I'm Julia Moriarty. Sorry, I was putting on the mics and didn't hear exactly what you said. So I'm sorry if I repeat it.
It was very short.
The three different, yeah. I'm an assistant professor at the University of Colorado in Boulder, and my research group focuses on using and developing models to better understand coastal processes, specifically sediment transport and biogeochemical processes, and the way they interact in the coastal environment. So some of the things we're motivated by are things like light attenuation. Ming before showed some of the harmful algal blooms in the Chesapeake Bay. Here's a picture of a turbidity following the storm, just to give you an idea of just how much sediment in the coastal region can impact light that's available for things like photosynthesis. We're motivated by things like shoreline change and sediment supply for wetlands. Here you see a marsh, but also in the tropical areas, mangroves, right? And then finally, interactions between sediment transport and more of biogeochemical reactions. So things like carbon burial in the seabed, how sediment transport impacts when and where organic matter accumulates and is either remineralized or decomposed versus buried in the seabed. And so one of the things I've been thinking about over the last year or two is how do we work in data-poor systems? So I have not worked in the tropics. I did warn the organizers before when they invited me to speak. I've never worked in the tropics. But I'm going to give some examples from the Arctic, which is also a data-poor system. It's data-poor. It's a remote environment. It's a remote environment. It's a harsh environment. It's often hard to get to different parts of it, and so its satellite observations are difficult near the poles, and so all of those things combine to make it a very data-poor environment. And then I'll also be talking about my second example will be oxygen exposure time. In contrast to the first example, which will focus on high-resolution modeling, this will be focusing on simplified modeling to try to calculate something that we don't really have a good way to quantify. And I'll come back to why this matters later on. And so for the rest of the talk, I'll be focusing on these two different examples as ways to approach problems in data-poor systems. Okay, and these are just two examples. I don't have all the answers. I wish we did. Okay, so with that, I'll start with the first one. This is work that's actually led by my PhD student, Brianna Unzus, who's shown here, and in collaboration with Emily Adam at Oregon State University and Irina Overeem, also at University of Colorado. And Brianna's dissertation is focusing on trying to better understand how sediment moves around the coastal ocean. And so we're motivated to understand this because it affects things like light attenuation. The Arctic has a lot of kelp systems where, kelp need light to grow through photosynthesis, but light attenuation is proportional to suspended sediment concentration in this region. We also are interested as the land in the Arctic there's a lot of permafrost, but as it's becoming warmer, the land is frozen land is thawing and releasing both dissolved nutrients and carbon through groundwater into the ocean, and also releasing particulate carbon into the ocean via coastal erosion. And so we are interested in where this material is going, whether the carbon is buried before it can be remineralized, or remineralized to turn back into CO2 before it can be buried. And so what we've been focusing on is trying to understand just the first part of this. When material erodes here, where is it going? Similarly, what's driving suspended sediment concentrations in the water? And this is complicated because we know that sediment transport varies in space and time, not just in the Arctic, but most places. You can get highly variable sediment transport patterns. This is an example from the Arctic where the length of the line indicates the potential for sediment transport. And so you can see these long lines here indicating there could be lots of sediment transport. Here there's like small dots indicating not very much. And these are regions that are right next to each other. So why? What's driving this? And so our work, and this is, as I mentioned, looking at this with the theme of limited data availability from observations and satellites. So we're going to look at some of these questions using numerical models. For this work, we used a higher complexity numerical model. I'll say a little bit more about it in a slide, but we're using the ROMS CSTMS sediment transport model. And so what are some of the processes when we're thinking about sediment transport in coastal areas? What are some of the processes we're thinking about, right? And so generally sediment is delivered to the coastal ocean via river plumes or shoreline erosion. And so once it comes out in the plume, it can settle to the seabed based on its settling velocity. And then, depending on the hydrodynamic conditions, it can be either prevented from settling, or it can be resuspended from the seabed back into the water column via energetic waves and currents, which exert stress on the seabed. And if the waves and currents are energetic enough, they can cause sediment resuspension. And so, right here. And so then when sediment is resuspended in the water column, whether it's in the plume, whether it's being resuspended, it can then be advected by currents along and across the shelf. Okay. So we wanted to use a model that could account for some of these different processes, very common sediment transport processes, and look at their relative importance in the Arctic to understand what's driving variability in sediment concentrations and transport. Okay, so to do this, we used the ROMS, or Regional Ocean Modeling System, which is coupled to the Community Sediment Transport Modeling System. And we did this within the COAST framework. So Ming showed us a schematic of COAST before. I won't repeat that, but we're just using the ROMS and system and CSTMS components, and then we also give it waves as inputs. So we implemented, here's our model grid. We're working on the north slope of Alaska up here. This is some of the highest coastal erosion rates I've seen, up to like tens of meters, like 10, 15 meters per year in some areas, which is quite a lot of erosion. So each of these grid cells is each of these boxes is 16 by 16 grid cells, and then we have 20 vertical water column layers and 11 seabed layers to account for the sediment. The model accounts for winds, waves, river discharge, larger scale currents through its boundary conditions. Sea ice is accounted for through the winds and the waves. And then we account for 5 different sediment classes. So we account for unaggregated mud, aggregated mud, very fine sand, coarse sand, and then a class that generally represents pebbles and boulders and sort of a more material that's harder to move. And each of these classes is characterized by a certain settling velocity, or how fast the sediment sinks in the water column, and also by a critical shear stress for erosion, which is how energetic do the waves and currents need to be to resuspend that material into the water column. Okay, so we implemented this model for the 2020 open water season. We actually, implemented it for 2019 and 2020. Since we're talking about data poor systems, when we started this work, we didn't actually have observations to validate the model with. So we actually started doing it for 2019, but we actually ended up switching to 2020 because the observations became available later on. And so we started modeling 2020. We modeled the open water season, which is the nearly ice-free season in the Arctic. One thing I want to point out here, you're looking at a time series of wind speeds, the larger scale currents, which is the currents that are going into the open boundaries, the significant wave height, the river discharge, the river sediment load, and the sea ice concentrations. And one thing I want to point out is that in this system, you're getting pretty strong currents, and they oscillate pretty frequently along with the winds. And also the one thing that became very important was that the magnitude of the currents doesn't really correlate with the locally doesn't really correlate with the magnitude of the waves. And so that became pretty important when we were talking. Okay, I'll come back to that. Okay, so when we implement this model, this is an example. Of what the model results look like. Here you're looking at a map of surface salinity. The shading is surface salinity. The arrows are depth averaged currents. Here you're looking at bed shear stress. So as you get to about this reddish and higher, you're able to resuspend sediment. And then here you're looking at the bottom, suspended sediment concentration. During this presentation, SSC is suspended sediment concentration, not sea surface chlorophyll. So I saw that acronym the other day. Okay, so one thing I want to point out is that the currents are switching directions, and that the bed stresses are relatively high on the inner shelf, sometimes on the outer shelf, but are episodic, right? So what happens is we have these wave events that come through and strong currents that come through and really cause bed stress on the seabed and then resuspend sediment near the, especially near the shore. Okay. Okay, these were slides in case the movie didn't work. Okay, so how well is the model doing, right? So I told you we initially didn't have observations, and one of the things that we did not do, which is not very typical, is we did not tune this model because we didn't have anything to tune it to. One of the very common things you do when you implement a regional model is you tune parameters like the settling velocity or growth rates or different parameters, depending what you're modeling, to match the local system. And we just simply didn't have the data to do that. And one of the things that was really neat is that it actually turned out okay when we got the observations. And so here, you're looking at, excuse me, you're looking at suspended sediment concentrations that were taken by Emily Adam's group in 2020. And here the dots are the observations of the observed sediment concentration. The shading is the model estimates of suspended sediment concentration for both 1 meter below the surface and 1 meter above the seafloor. And so you can see that the model captures the generally the observed magnitude. I am not plotting this on a log scale, which you may also see when you do model observation comparison for sediment. It's often done on a log scale. This is on a linear scale. And it represents the across-shelf gradient pretty well. Okay. And then again, I wanted to point out that this is without model tuning. Oh, why is this? Okay, there we go. And so, however, I do want to point out that our forcing, the model's not perfect, right? And so when we look at the currents and the waves, you can see some of this variability. Here you're looking at the observed wave heights and peak period. Here's the modeled wave heights and peak period. This is the same thing, but at a different station. And we do some, the model does underestimate the waves a bit in general, though it overestimates them here. And so this is not perfect, but it was good enough to get the suspended sediment concentrations. And so we could then use this model to look at things like what is driving resuspension on different parts of the shelf. So here what you're looking at is the bed shear stress. So it's higher, you have more sediment, you can have more sediment, you have more energetic waves and currents, you can have more sediment resuspension. You could then break it up due to the bed stress due to currents and the bed stress due to waves. These are in %. And so you can see that most in the inner shelf, most of the bed stress is due to waves. On the outer shelf, you have these strong currents that go along the slope, the elastic coastal current, and not surprisingly, that exerts stress near the shelf slope break. But when you look at the magnitude of the bed stress, in how frequently, and then sorry, on this bottom panel, you're looking at the fraction of time that bed shear stresses are above the critical shear stress for erosion. And so here you can see that on the inner shelf, sediment can be suspended, up to 50-60% of the time in some areas. It's more resuspension within the 10-meter isobath, and that can be attributed largely to waves. And then with a little limited resuspension on the shelf slope break. And this is similar to patterns you see other places of the world. Okay. We can also look at where the sediment is going. So before I pointed out that the waves and the currents weren't correlated, right? The timing of them they weren't occurring necessarily at the same time. And so one of the things we found is that here you're looking at the shading is the magnitude of the depth averaged current. The arrow is the magnitude and direction of the depth averaged current. And on the bottom, you have the shading is suspended sediment concentration. The arrow is the depth integrated suspended sediment flux. And one of the things I want to point out is that along the shelf, in a lot of areas, you have a general eastward current, right? Pretty much most of the shelf, a little bit not here, but definitely on the outer shelf, also here. Whereas the sediment fluxes are generally westward, right? And so this is a little unexpected. I see a little bit of people making faces in the audience. So why is that? And that's because the energetic waves are preferentially occurring when the currents are eastward. So what we were talking about yesterday, where getting the mean values isn't always good enough, this is another example of that, where if you just use the value of the mean current, you would get the sediment fluxes in the wrong direction. Whereas when you look at the currents that are actually happening when sediment's being resuspended, that gives you sediment fluxes in the opposite direction of what you would expect. Okay. We looked at this using scatter plots as well as sensitivity tests. And so here you are looking at scatter plots of significant wave height on the x-axis, the depth averaged current on the y-axis. Positive is eastward, negative is westward. And so in general, the shading of the dot indicates the magnitude of the suspended sediment flux. And so in general, you're getting higher suspended sediment fluxes when you have higher waves and also strong currents. And in particular, you're getting these really, especially on certain parts of the shelf, like the western shelf, you're getting really strong sediment fluxes where you're getting high waves during eastward current events. But you don't see something similar up here. You don't see these high fluxes during eastward current events, just westward current events. Okay. Okay. And so some of the things that we've concluded using this model are that resuspension was driven primarily by waves on the inner shelf and occurred up to 60% of the time from mud and fine sand. And it was highest, there were also highest suspended sediment concentrations on the inner shelf. And then on average, suspended sediment fluxes on the inner shelf were westward despite eastward currents due to the timing of waves. We also, going back to the first one, I think it's noteworthy that we just implemented this model and that it did fairly well out of the box without having to tune the model. And so I think this is a good test of the model's capabilities and is being able to use it in a data-poor system. Okay. The second example that I'll show is focused on oxygen exposure time. And so here we were motivated by the fact that in coastal areas, especially deltas, less carbon is buried than would be predicted to be buried. So here you're looking at a scatter plot of carbon burial efficiency versus sediment accumulation rate. Generally, these things are proportional because if you bury carbon quicker, it gets out of the oxygenated zone of the sediments more quickly, and so it gets buried instead of being remineralized. And so in general, these things are proportional. However, what you can see here is this group of points, and this is on a log-log plot, you can see this group of points that's about half an order of magnitude to an order of magnitude less burial than you would expect. And so the question is, why is that? And for a long time, this paper was written in 1998. For a long time, this has been thought to be due to the exposure of oxygen due to resuspension. So if you have organic matter that's constantly being resuspended, it's exposed to oxygen. You also have mixing in of labile organic matter, and all of that can stimulate remineralization of organic matter. And that's been thought to account for this decrease in carbon burial. And this has been supported by correlations between organic matter properties and rates of resuspension and oxygen availability. There's also been a lab experiment that shows that resuspension can increase the remineralization rate constants, or how quickly this organic matter is being remineralized. But one of the things that's really held back a mechanism for quantifying this is that we don't have a good way to estimate oxygen exposure time in environments where resuspension matters. And so historically, oxygen exposure time has been calculated assuming that resuspension does not occur, that you can calculate oxygen exposure time as the time it takes for a layer of sediment to be buried, to transit from the top of the core down to below this oxygen. The coloring indicates oxygen is present, so below this layer here. So it's been defined as the time it takes for a layer of sediment to transit through the oxic layer of the seabed. And that's generally calculated by dividing the oxygen penetration depth, or OPD, divided by the sedimentation rate. So just how long it takes for that layer of sediment to move through the oxic layer. However, we know in coastal environments, this is an example from the Rhone Delta in France. We know in coastal environments that sediment is often resuspended. You can get centimeters of resuspension commonly in coastal environments, and that's resuspending material from the anoxic portion of the seabed into the oxic water column. And so here is an example from the Rhone Delta. You have bed stress on the top panel. This is a time series over 2 months in 2012. This is model data, but there's also observational data. We were working closely with Christophe Rabouillet's group at CNRS in France and his student Flora Toussaint. And so there were 3 wave events that generated peaks in bed stress. And those, on the bottom panel, you're looking at seabed elevation, so you're getting erosion when there's bed stresses, right here. This red dashed line is how deep the oxygen goes. It's your oxygen penetration depth. And so anytime you have resuspension, when you have the seabed dipping below here, you have erosion below the oxygen penetration depth, that's a time when you're taking sediments from the anoxic zone and resuspending them into a relatively oxic water column. And so we know in coastal environments this happens relatively frequently. And so the question we're trying to answer is, what is the role of local resuspension on oxygen exposure time? And so what we did is we took this time series, we looked at how frequently each layer of the seabed was resuspended, came up with this graph here. So this is depth into the seabed versus resuspension frequency. This red dashed line is the oxygen penetration depth. So you can see here, this blue line, it's more likely you have resuspension near the surface of the seabed. By the time you get about 2 centimeters in, you have near 0 resuspension. And then we can integrate, this is my bad the PowerPoint skills, but you can integrate between these 2 curves to estimate the resuspension-induced oxygen exposure time. And so you can then add this to the oxygen exposure time that can be calculated using the former method that doesn't account for resuspension, and use that to get the total oxygen exposure time. We found in general, ignore the difference between the turquoise and blue lines for right now. I'm going to come back to that because we were trying out different methods of calculating this that could be applied in data-poor systems, so I'm going to come back to it. But right now I just want to show you that here you're looking at the total oxygen exposure time if you don't account for resuspension, versus in the blue and turquoise if you do account for resuspension. And then in this environment in the Rhone Delta, accounting for resuspension doubled the amount of oxygen that any organic matter associated with the sediment would have been exposed to. And then we could do sensitivity tests that show that if you have a thinner oxygen penetration depth or more resuspension, then more of your oxygen exposure was due to resuspension. And I just got the 5-minute warning, so I'll, I think, okay, let's see. I'm good. But one of the things that I wanted to point out is that this whole method is based on having a time series of seabed elevation. So that means you either need to have a model that will predict it, or you need to have some sort of like acoustic instrument out there measuring variations in the seabed, right? These are not that common observations, either way, or common model. It's, it's hard, it takes a lot of time to implement a model. They're not common observations. So what can we do in other systems? And so, so what we started doing was seeing if we could use something called Rouse profiles, which is a more idealistic way of estimating erosion and deposition, and seeing how well this worked in this environment. So what Rouse profiles do are they assume that there's a balance between the downward settling of sediment and upward turbulent motion of sediment, and so then you get you can get an equilibrium profile of suspended sediment concentrations, and if you integrate over the water column, you can use that to estimate the volume of suspended sediment and how much erosion there was. This makes a lot of assumptions. You're assuming there's no lateral transport. You're only accounting for what's happening vertically. You're not accounting for processes like seabed cohesion and other processes. But it can be applied in a variety of places with commonly available data, such as information about waves, information about currents, and information about like grain size and some seabed characteristics. And so we did this for, this is just the same thing in a little bit different form. So we started using waves and currents to estimate bed stress, and then estimated a Rouse profile, and used that to estimate the seabed elevation. And when we do that, it looks sort of similar. So here's your resuspension frequency. This blue line is the standard model that from the ROMS model. This turquoise line is the Rouse profile. And you can see they're sort of similar. And more importantly, when you estimate the effective resuspension, you both get a substantial change in the oxygen exposure time due to resuspension. It's not perfect. And one of the things we're continuing to do is look at when and where this can be applied, when and where it can't, how well it does, and just testing the limits of this approach. But that's where we're going with this work. And so this is a very different approach to working with data-poor systems. And then this movie, unfortunately, doesn't work. But we're going to likely use high-resolution models to investigate this in a more idealistic environment. Okay, so in conclusion, local resuspension about doubled oxygen exposure time at the Rhone Delta site, and this estimate was conservative due to neglect of lateral transport. And then we saw that results based on Rouse profiles were similar to those from a complex hydrodynamic sediment transport model. And it could be more widely applied, though we need to do some more work quantifying the error in this case. And then I just wanted to end with a few lessons learned overall. We saw these were two, inspired by the conversation yesterday. I focused on things that, we always talk about the uncertainties. This is a case where the models did do a pretty good job even without data availability. And so we saw that a process-based high complexity model could represent suspended sediment transport in a data-poor environment, specifically the Arctic. And then low complexity models could perform well for specific applications. But more work needs to be done to quantify uncertainty in these data-poor environments. With that, I'd just like to thank my lab group, Brianna Unzis, Tina Geller, Krista DeSantos, and collaborators, Emily Adam, Irita Overeem, Melissa Moulton, Alex Yan, Wei-Xing Han, Chris Jenkins, Dongmei Feng, Shoy Lee Rahman, Tian Gan, Eric Hutton, and Greg Tucker, and then funding from NSF and CU Boulder. I'll leave it there.